Hey physics class, sorry I can't be there today, but I'll do my best to describe to you the working components of a Stirling engine in this video. So let's start by talking about resistance. We can think about electrical resistance in the same way that we can think about heat resistance, such that the farther that the electrons have to travel, the less energy can be extracted from them into and across whichever medium you're using. So if you have a filament that's very long, its resistance will be a lot higher than a filament that's very short. Now with the metal, in the parts we're describing, the top plate of the Stirling engine and the bottom plate of the Stirling engine, the metal is very thin, so the electrons have a very short distance to travel, meaning that these plates can extract all the heat energy that they need to. Okay, so we all should understand the functionality and properties of the top plate and the bottom plate. And now I would like to describe what this white bit here is. And it is called the displacer cylinder. It is actually made of styrofoam. And this is important for two reasons. First off, the displacer cylinder needs to be easily manipulated upwards and downwards, so it can't weigh a lot, and styrofoam is very light, so it's perfect in that respect. And second of all, we need an insulator in here. And the necessity for an insulator arises from the fact that this engine can only function due to a temperature differential, which Patrick will elaborate on more. So back to insulation. We can imagine that if this cylinder was just empty of the displacer cylinder within, it would just be a pocket of air. And if we placed a heat source underneath, such as this hot coffee cup, it's not actually hot right now, but in the demonstration we do in class, you'll see how heat can actually get this thing moving. But regardless, the convection currents inside here would radiate heat outwards away from this central input of heat. And that is actually one of the primary losses for heat transfer across an air-filled space, is natural convection. So to eliminate this, we use an insulator, such as styrofoam. So how does styrofoam act as an insulator? First, it traps the air so these convection currents can't form, and heat loss is eliminated in that respect. So now you have conductive heat loss and radiative heat loss. And styrofoam cleverly capitalizes on the fact that air is a very poor conductor of heat, so it fills all the tiny cells within styrofoam that make up a piece of styrofoam with air. So now styrofoam has the conductivity of trapped stagnant air, which is very low, and almost a negligible amount of heat is radiated from the styrofoam, as the very outer surface of these cells eventually will match the surrounding ambient air temperature, and little heat will be transferred. So how do we measure insulation, and how do we know that styrofoam is a good insulator? Well, there's something used in the construction and building industry that is called an R value. An R value can be calculated by the ratio of the temperature difference across an insulator. Across an insulator meaning the height or width or thickness of this insulator, particularly styrofoam. And you usually use the R value in correspondence with an inch of the material you're measuring. So styrofoam boasts an R value of 5. To put that in context, 1 inch of concrete has an R value of 0.3, wood 1 inch again, 0.91, fiberglass 3.9, and cork 3.57. So now I will talk about viscosity, which is a fluid's resistance to flow when it is experiencing some kind of deformation or stress. So in everyday terms, we can think of viscosity as internal friction or a fluid's thickness. So an example of this would be water having a low viscosity because it flows easily out of a cup, whereas honey would have a very high viscosity because it takes a long time to flow out of a cup. This is important because the fluid that is within this cylinder needs to be deformed and compressed and expanded over and over again. So therefore, the lower viscosity it has, the easier these deformations can perform, and the less friction the machine will feel, and the higher efficiency it will have. So we can put viscosity in context by using the measure of a gas's kinematic viscosity, stemming from the word kinetic, because a gas is just full of a bunch of molecules with kinetic energy bouncing around, exerting pressure on whatever they come into contact with. And kinetic viscosity is measured by observing the length of time it takes a fluid to pass through the orifice of some standardized capillary size under the normal force of gravity. And to put viscosity in context once more, relating to specific gases, I used a calculator online, assuming that the temperature of the gas in here would be around 70 degrees. Came up with air having a viscosity, kinematic viscosity of 1.993, helium 1.532, and H2O, which would be steam in this case, is 4.029. We can see that steam would be a very poor fluid to use, and helium would by far be the most ideal working fluid to obtain the lowest viscosity and greatest ease of movement of the working fluid. So now, before it is Patrick's turn and my turn is up, I'll quickly label all the working parts of the Stirling engine and go through one cycle. I've already talked about the top plate and the bottom plate, the displacer cylinder, the working fluid within. This part is called a power cylinder, in which rests a power piston. And you can see the black piston moving upwards and downwards. The piston is connected to the power piston connecting rod. This connecting rod is attached to the axle. The axle is attached to a flywheel. And on this other side, the axle attaches to what is called the displacer shaft, which you can see directly exerts a force on the displacer cylinder. And now we'll go through one cycle of movement. First, keep an eye on the displacer cylinder and the piston. As the displacer cylinder is pushed upwards, the piston eventually bobs upwards and sort of floats in the top of this power cylinder. The power piston then exerts a force on the power piston connecting rod. You can see when I move the power piston connecting rod up and down, it spins the flywheel. With the flywheel spinning and storing rotational energy, the axle spins with it. And following the flow of forces exerted, the axle then exerts a force on this rod called the displacer shaft. The displacer shaft then pushes the displacer cylinder up and down as the shaft moves up and down. So they move in harmony, the wheel and the piston move in harmony, and that's one full cycle of movement.